Okay, so welcome back everyone. So this is our last seminar for this quarter. Uh, and today we have the pleasure of having Minger Xie. Dr. Xie is a distinguished professor at Rutgers University in the state of New Jersey. He received his PhD in statistics from University of Illinois at Urbana-Champaign. Uh, he's currently the editor of the American Statistician and co-founding editor-in-chief of the New England Journal of Statistics and Data Science, a fellow of the ASA and IMS, and his research interests include theoretical foundations of statistical inference, data science, vision learning, finite and light science theories, and he's also the director of the Rutgers Office for Statistical Consulting and has experience not just in theory, but in interdisciplinary research, collaborating with computer science, engineers, and biomedical researchers and other things. So do you, so the floor is yours. Let's start. So just one a question about admin. Do you prefer questions during or in the end?
Either way is fine. What's your convention?
I guess during it would be easier. So I'll let you know
Okay.
5 minutes before we're close to the
Okay.
to the end. Okay.
Okay, great.
So well, let's welcome our.
Okay, thank Carlos for the nice introduction, and then thank Abel, Carlos for the invitation. I'm really delighted to have this.
Just delighted.
Okay. I'm really delighted to have this opportunity to how come I okay. I cannot move this one. Oh, okay. No. Oh, okay, no, it's okay. I'm really delighted to have this opportunity to visit this wonderful department. I know this department for a long time, but I never get a chance to visit. It's a really nice opportunity for me to be here. I'm really glad to have the opportunity as well. So here, what I'm going to talk about today is something a little bit new in the sense is that the title is talking about Fisher inversion, Repro samples method, and particularly use the random forest as example, how the tree models to how to do this. Here are the wonderful collaborators of mine, and then I really I really like to work with young people, and I learned a great deal for each of these young people. I think some of you probably know this few young colleagues of mine. Today, what I'm going to the mostly is coming from this principal random forest is ongoing research. This is with a PhD student, Zhengyu Wang, and also my colleague, Zijian Guo. But then the other, more like the development lab inversion and then Repro samples method that actually has a long history. Well, has a lot more history. And then this is other collaborators kind of involved in this type of research. So I'm limited, but to me, as an inference person in statistics, doing statistical inference, thinking about inference problem, the big challenge in statistics in data science nowadays, to me, it seems one of those things is the to deal with inference problems in which the regulatory condition does not hold. The regulatory condition hold, in particularly, we cannot use large sample theory for those things, and also the likelihood inference probably is not available. So this is actually is coming together with like Larry Westman's PNAS paper on he was motivating how he was doing the universal inference is that I don't have regularity conditions. I don't have central limit theory. How do you do that? But they are still using likelihood function, but I don't have likelihood function. Part of the reason is because in the data science problems, you do have parameters are discrete. And then also even non-numerical. So your data could be number of clusters, number of neighbors, number of nodes, things like that. And tree partitions model ABC. So this could be the parameters, model parameters itself is non-numerical, is discrete, numerical, or non-numerical. And also your data, we know that we have graphic data, voice data, and things like that. The data itself are also could be non-numerical. So in the sense is how do we do the inference with this type of things? That's basically our problem. I'm going to give you a few examples of what we have been, our group have worked on, and then you can see that type of problems, what was the issue. And then the first example actually we work out first is a classical kind of Gaussian mixture component. You say, hey, I can use AIC, BIC to do that, hat, K hat, tau hat. But the problem is that what is uncertainty associated with it? Do you have a confidence interval of that? So it turned out to be very, very difficult problem. Is that because, well, maybe later on I will talk a little bit more. And the second thing is that we just got the actually this NIH grant to work on these things. Is that you can just imagine I have a graphic model, which is that observed a graph. You can just imagine we're using that actually on the gene network, but you can kind of explain this when you use the COVID network. So you just see a network of COVID infected patients. And then the idea is that can we find a patient zero, a group of patient zero? Can I get a confidence set of patient zero? Who are those people of that? And the notes of a graphic of this kind of graphical network is that this is actually, its graph itself, it's probably is not the traditional data, is a matrix, right? In statistics, your textbook, typically you have X and Y. Your N times P, right? That's your data matrix, or maybe array. But then this actually graphical network, it's not, it's a list of things, list of features, list of nodes, and things like that. And then it's not the traditional form. And then the other thing is the harder part is that the nodes, who are the patient zero. So for original nodes of started with COVID infection. So that's kind of things. And then with identify those things and also do the to identify those things or uncertain quantification about it. Do you have a confidence set to tell me 95 confidence it's coming from this particular group of few patient? Today, what I'm going to talk about is that as a tree model. You can just thinking is a tree model. Tree model, we are looking at a regression tree model. And this regression tree model actually turned out to be mathematically, you can write it out. It's very similar to the Gaussian mixture, to the mixture model. If you have noise, Gaussian noise is very similar to the extension of Gaussian noise model, Gaussian mixture model. But then the harder part is that each tree corresponding to a space partition, covariance space partition. So the model parameter, including the partition space, right? That's you have suppose I have a true tree model. You're coming from the data coming from a true model with membership according to this true particular partition. Then the question is that this is object. And how do you get a confidence set of this object? And then if we can get a confidence set of this object, actually today I'm going to show you how we do that, is that when we get a confidence set of the things, instead of do the random forest of all the trees, possible trees using other things, we can use the inference to prediction to ensemble trees, only use those trees in the confidence set. The confidence set is a lot smaller. Actually, we have example looking at these 50 trees. 40 trees instead of looking at 1,000 trees of you doing that one. And this is actually the result is more, we call it principled random forest, and it's more effective. And this actually is a problem in the in our proposal is talking about the deep neural network model. Deep neural network models actually mathematically you can write out mathematical models of, although this is over parameterized, and this is over parameterized model. And then the model parameters, you do have one of the things that's very interesting is the architecture model. Architecture parameters is that tell you how many layers, how many number of neurons of doing that. And the question is that can we get a confidence set of architecture parameters? Is a confidence set of smallest neural network that with how many edges, how many layers, how many neurons will give me that result will look like the picture, the cat we got. And if we can get that, then the inference, right, in the black box model become a lot more clear. Black box model is that we do have observed data, and we try to infer what's going on. That's statistical inference is doing it. But right now is everything's black box. Is that because we don't have proper statistical inference tools to deal with those kind of very complicated discrete parameters. If you have a way to do that for each of those structures in this kind of in the confidence set, then you can look at each interpretation of each model. So that's make things a little easier. The same thing in the tree model. So the other thing actually we did, this is actually one of the things we kind of trying to look at post-selection inference. We have you have expert in this department of talking about the post-selection inference of things. And then this is one of the problem in the high dimension regression. Actually, we started these things in one of those post-selection inference. We're talking to Peng Wan about this problem. And then we realized, and then we think we have a solution to it to sidestep the topic of post-selection inference. So the problem setup is that suppose I have high dimension regression model with sparse models, right? Of course, you don't know sparse model. You can use lasso or whatever algorithm to get those tau hat. But the question is that how do you quantify the estimated model? Your lasso model, you have estimate of that. You post-select inference, you conditional on whatever selected, and you do the inference, right? But then the question is that, do you know the uncertainty of this tau hat itself? So the question is that, can we get a 95 confidence, this is alpha is 95, confidence set for the true parameter of interest? Can you do that for this tau 0? Not just the hat, and give a confidence set of the model. The other thing is that for each of the confidence set and how about the parameters? People typically doing the d-bias is one scalar parameter of beta. And then we can actually doing the either scalar or subvector or the full vector of the parameters to the inference we will be able to offer. And even we can do the joint inference of this model and model parameter. And the performance actually we have worked out both finite larger sample theories. And then in the sense that in typical high dimension regression, we do need to have n goes infinity. And then actually our theory guarantees that even n is finite, p is finite given, then we still will be able to get legitimate confidence set of these three group of parameters. So, but anyway, so this is kind of something is that it started with try to address the post-selection inference. The issue of post-selection inference is that if that important variable is not selected by your post-selection inference, you won't be able to, you'll miss it. You won't be able to, you still have some chance to miss it. And if you miss it, then you won't be able to do any beta inference of that. The empirical evidence actually turned out to be better than d-bias method when we do the single beta, but I don't have a chance to do that. And refer you guys to our archive paper to talk about the discussions of this. But in any way, so this has been a bunch of papers we're working on, and then the things using these techniques to do it. The very important question is that why we need to have this so-called new framework. What we were doing, trying to do, is that we have already existing statistical inference framework, like a method or other method, why or a Bayesian method or point estimates, why we need something else. So this is actually in statistics how to make inference of such parameters. Such a type of data, like if it's discrete, is not continuous, right? Your parameter is not in the space of continuous parameter space. How do you make inference? For example, the point estimator, even in the Gaussian mixture model, even your point estimator, AIC, BIC is consistent. But then you still do not have node uncertain quantification. If you have used BIC in practice, actually I did when I first started my job, as BIC was in my simulation, 60% of time getting right. I was worried, and then people tell me 60% is already very good if you get the BIC to estimate get it. And then that's basically, that's the thing. And then what is uncertain quantification associated with it? Instead of getting one single K, we get a set of Ks. So this could be mixture of 2 or 3, 4, instead of just giving you one number 2. And the bootstrap estimate does not work. A lot of people actually using bootstrap. Why the things bootstrap does not work is that because in the discrete parameter space, central limit theory does not, tau hat, you don't have central limit theory space because it's on discrete parameter space. If you have bootstrap, your bootstrap estimate the tau hat put in there, there's no central limit theory. Bootstrap, why it works is that you have artificially generating your bootstrap samples. The bootstrap sample is artificial sample. Artificial sample is coming from what the randomness is, a multinomial randomness. And then you have multi-normal randomness, and your sample randomness, your target, it could be from, for example, from geometric distribution. So geometric randomness and the multinomial randomness won't match to each other. How would you kind of line up these two? Is because of the central limit theory, right? Multinomial has central limit theory, geometric distribution has the central limit theory, and you put them together so that the artificial randomness and then sampling randomness match. So I can use bootstrap to do it. Bayesian actually is easy. vehicle to do the credible set of those discrete parameters. But there are two issues of that. One thing is that very sensitive to the choice of your priors. For example, I have model ABC. Is that 1/3, 1/3, or it is a half, quarter, quarter. So that's kind of give you quite different results. So that's priors is very sensitive. Actually in the Gaussian mixture model, I was asking Jim Berger which kind of good priors to have. He give me some sort of power law kind of prior, but then let's say it's still very sensitive, but that's probably the best you can do. So that's basically, that's the thing, is very sensitive to the prior choice. Different priors will be different. And then the other thing is that typical, as a frequentist myself, I typically like to see the frequency coverage. For Bayesian, even I'm using a Bayesian method, I use a Bayesian method afterwards. I want to check the frequency coverage. And in this particular case, I won't be able to use the frequency coverage because there's no guarantee, because the Bernstein-von theory does not hold. My understanding is that most of this proof of Bernstein-von theorem, when you have n goes infinity, the prior information gets less and less, kind of washed out. So it's more like likelihood. The likelihood of central limit theory that works. So that's pretty much is like the Bayesian version of that would work as a frequentist coverage. But in this case, I don't have central limit theory. So the BVM is not working. So I don't know whether that will be checking the frequency. Empirically, actually, the frequency coverage is pretty poor if you use Bayesian method to do that. The Gaussian mixture model, in our paper, we have that examples. So in these things is that basically we typically traditional have been using is not really working. So what we do is that we use a simulation inspired artificial sample method. This is actually has to do with the Bayesian bootstrap. Actually later on next slides, I'm going to say where intuition coming from, but it's more artificial sample inspired generalized method. This method is very general, can apply to the usual regular inference problems, including traditional settings. The parameter is continuous. But then this things is you already have the central limit theory, large sample theory, or Bayesian or other method is really working well. So this is not really advantage. Really advantage is the situation is that making inference, my result is trivial, non-irregular inference problems. Like I have a discrete parameter, I have a parameter is object, or my data is object. So that's basically the thing. So this is actually, before I give you go to the mathematical kind of formulation, general formulation, mathematical formulation, how we do it. I probably want to give you intuition, the key ideas behind it, what we did it. Actually, this is probably Abel and many of you know that I'm working on this so-called BFF kind of group with this associated with this group Bayesian fiduciary frequent, trying to connecting all these three paradigms or understanding each other. So one of the things I learned in the BFF, well, I learned this, and in this kind of context, the BFF context is approximate Bayesian computing. This is, I would say, hey, this is a really amazing method. I actually asked Abel about this as well. And then this is, you can get your posterior distribution without using a likelihood function, without using the base formula. So how could you get posterior distribution without posterior? So this is actually using the artificial sampling method to do it, and also has this kind of so-called Bayesian inversion kind of idea behind it. So what to do is that my model is very complicated. Likelihood function is not easy to get. I might be able to get, for example, use differential equations. Likelihood function is not easy to get. And the model, yeah. And then what you do is that I use prior. I simulate something from the prior distribution, simulate theta star from prior distribution. And then from using this theta star, using the data generating equation to get a sample, kind of artificial data. If the summary statistic is artificial data, sufficient summary statistic of artificial data is very close to the observed summary statistic of observed data. If their difference is less than epsilon, then I keep it. Otherwise, I throw it away. So that's basically ABC, kind of rejection version of ABC. And then it turned out to be, if the summary statistic is sufficient and epsilon goes to 0 faster than square root of n, then this theta star, what you kept, is coming from posterior distribution, even though you don't have you didn't use the base formula. So that's kind of amazing. First, I learned about this. This is very intuitive because in practice, in real life, we do the same thing, right? We get something, try it. If it works, I keep it. Otherwise, I don't. That's the same thing what the Bayesian is doing that. So my question is that, can I have a frequency version of that? because the understanding is that Bayesian version is anything Bayesian has, frequency probably have it. And anything Bayesian, frequency have it, Bayesian probably have similar version. So that's kind of idea to be, between that. So in this case, so in this situation, sorry. So in this particular case, then we just say, hey, how about the frequency version use artificial data to do it? So that's kind of start our research of this particular development. So one thing is that I was talking to a group of people, professors from CMU. So they are expert on conformal. So they asked me, what is your exactly intuition behind it? I said, oh, you guys are doing the conformal, the expert on conformal. Maybe I can use an oversimplified situation to explain that. So I don't know which parameter should belong to my 95 confidence interval, but I say, let me try one of the particular theta. And they use this particular theta at generating 100 sets of artificial data. So each artificial data, right? I look at the summary statistic. I have 100 number of summary statistics. But the observed data, I also have one summary statistic. If this observed data set, observed summary statistic is conformal with 95% of confidence belongs in the middle of this 100 artificial data points, that I keep the theta, otherwise I throw it away. It turned out to be, you can easily prove the theta you kept is form a 95 confidence set. So that's basically very intuitively, that's the idea, is that you're generating artificial data, and if that true observed one is within the range of your artificial data, then the theta might be used right. I keep it, otherwise I throw it away. So that's basically, that's kind of idea of that. But of course, mathematically, when you see that, there will be a little bit different, and the more in connecting to the Fisher inversion approach. Later on, we'll talk about Fisher inversion kind of idea. That's essentially is that one. So nice thing about this thing is that we prove the frequency performance, and then the really important application is that suppose I do have theories involving the discrete parameters, the model problem setting, I can deal with that very relatively easily. So I'm going to talk about that as example. And then the nice thing about it is that feature is that part of the reason is the optimization, the kind of we can optimization programs getting together. Okay, so let me just skip this slide. So it's one thing I want to say it. This actually just last bullet. You can treating the classical Neyman-Pearson test using the inversion to get confidence set would be a special case of what we do. In the sense is that anything they get, if it's optimal, we can get the same result, get same confidence set. If the classical test is not optimal, they get some confidence set. This Neyman-Pearson does not necessarily always give you the optimum intervals. In that case, we actually usually can improve it. So that's the sense we will do better. And then before I move to the things, this is a slide when I give a presentation in the UPenn biostats. I kind of, they want to see evidence before you kind of listen to the theory, to the models. So one thing is that I can say, hey, let's see the evidence of it. The evidence is that suppose I'm doing the simulation, I have a true model, my data is coming from this tree. And then so this is basically my tree model, and this is my tree, how I generating the data. One particular things is each leaf I have different means. This is a 2, this is a 0.2, this is negative 0.2. So that's kind of thing. So the idea is that I want to predict the new y, which is coming from the new x new is this. I know the true, by this model, I know the truth of this is negative 0.2. But of course, then assuming I don't know this, right? The true parameter I don't know. So I want to predict negative 0.2. If I use the traditional random forest, I generating like 1,000, like from this data set, I get one set of this data set, particular data set generated from here, I fit in a random forest. If I do the random forest, that's kind of, I get 1,000 points, 1,000 predictions, 1,000 trees. Each tree, I will give you a mu new prediction, the prediction. And with that, I can plot, I use a histogram. I plot a histogram of this 1,000 points. And then you can see that the 1,000 points get kind of spreading out. On average, the truth is this dashed line. So take an average of this histogram, you still get this thing. So you know the random forest is consistent. That's okay, I get the result. But then the random forest 1,000 trees, bunch of the trees are pretty under-predicting, and a bunch of trees are up-predicting. So that's basically, you use that among those 1,000 trees, some of them are pretty bad. Some of them okay in the middle, the blue points, right? But a larger percentage of them are significantly worse. So that's basically what they do. And then the random forest. If you use the random forest for the point estimator, you take an average of these things. So basically, you do the average of those points, then you get to the point estimator. We call it this. And then if using our method, instead of using 1,000 trees, what we do is that we use our method to get confidence set of those. Based on the same data set, we get a confidence set of trees, or it's principled, kind of a lot smaller. Our confidence set of the trees, or estimated trees, is going to be like 50 trees, 40-some trees. Yes?
So in terms of the specific trees, the random forest basically never gets a tree in your confidence set,
right? Well, actual tree might be one of the trees in the 1,000 trees, but one of them might be right. But then you have a lot of others.
Yeah. I bet none of them. I bet you rarely get ones right because you're just picking them randomly, right?
Yeah, picking a random sampling is harder. It could potentially there's one right. Yes.
Yeah, you might.
You might get there, but then this is kind of a lot of these bad ones. Yeah, the bad ones. Yeah.
Yeah, I just from the perspective of interpretation.
Interpretation, right?
Yeah.
You don't get good trees, even there's consistent estimate, like an average, but then you don't get, you shouldn't get, So what we do is that we get confidence set of the trees is become 50 trees. And with this 50 trees, you can see that I have 50 points, kind of histogram, you see that. They are much closer to the truth, to the center, to what you do. And then you would be expected the performance is good. And then the one thing actually we did numerical performance with repeated 300 times, right? So for each of these, you take an average point estimate of the blue trees, then get a point estimator, look at the -2. Look at how good they are. There's a mean square error is. Then if we use this our principal random forest of using take an average of 50 trees and get that. So you see that 1 in 1,000 is a lot better than the random forest. And when n goes increase, is even better. It's about 3%, 4% of the mean square errors. So with our method, it's actually numerically very good. The part of reason is that, of course, our assumption is kind of the truth is coming from the tree. If the truth is not coming from tree, something close, the ratio is not as good, but it's going to be better. Still be better, but not as good as this one. Okay. I don't. It's just that simulate a data set that I just use the tree to go to we just off the shelf kind of algorithm to do it. We didn't fix number of split, no. We don't know the number of split. That we let the data to tell me. Yeah. Okay, so that's basically that kind of numerically. You can see that's the improvement of that particular our method is that more principle looking in the middle of the trees. So this is kind of the idea how we are kind of doing that. We started the mathematical formulation. We started data generative equation. And so this is I have a data is generated from my model. The G is no model. So it's for example it's a high dimensional regression model. You can think of the G, and then it just G is just this version. G is just this version. Yeah, put in there, right? So basically, you give a true parameter, give you a random noise, then I can have my observed data. So that's basically generated model. Any of that, and then the typical regression textbook is the same thing, right? You have a density, then you can invert it, do this way. And then later on, actually, more recently, we realized that even this kind of framework can look at AI, pre-trained AI models. Even this is G could be pre-trained black box model. I can still use that framework to do inference. But anyway, that's something we're not going to do that. The minimum assumption of these things is that given parameter, I would know how to generate in the corresponding Y. That's all I need. So that's basically, that's all I need, the framework. The goal is that to guarantee the level 95 confidence set for the parameter of interest. And the parameter here, when you do this, is it can be any type of parameter, continuous or discrete. And this is actually one of the method, probably one slide is that probably can give you some intuitions why we mathematically why it works. So you look at the model, right? The realization is that I observe data, there's truth, and then this is realize the error. This is exactly equation. If you kind of looking at that one, the uncertainty of Y is all coming from the U because I'm frequentist, the theta is fixed. So the noise, random noise coming from U. When I model quantified uncertainty of y, it's a lot harder to quantify uncertainty of u, because u does not involve in theta, doesn't involve in the truth. Okay, so the idea is that let's first do the confidence set for the u. Because I know the distribution of u, so it's easy to get a broad set satisfy this condition. So basically I can broad set satisfy this condition. Then what is my theta is going to be? I try all the theta. If I can find a realization in this broad set such that I can generate my observed data, that means the theta I cannot throw it away. So basically that's kind of, if I have this broad set defined to control the noise of the u, then I just use this formula to create my confidence intervals, confidence set. Intuitively is basically for any potential theta, if there exists artificial realization, that realization may not true, but then I can generate artificial realization in this broad set. It is kind of easy to get set, common set. Then I have a general artificial data. And this artificial equal to the y observed, exactly match actually. Then we cannot rule out the theta is the theta true, theta zero. Right, you just say, I know the truth that the observed data is coming from the true parameter and then some realization. Then the question is that if I can find the realization, and then I can generate this data with this particular theta value, then I can find another realization with the particular theta can get exactly the y observed. That means this could be the truth too, right? This pair could be truth too. I cannot throw it away. Okay. The only thing is control that noise. Is that noise I need to control into the broad set. Okay, so that's why I don't get crazy kind of U stars. Okay, so that's the idea. The proof of this thing is just few lines. This is exactly kind of inversion idea with this artificial things. But then the things is that doing this sometimes is not that easy. And then because this is kind of n-dimensional, right? You want to have a reduced dimension. So that's kind of, we do the summary statistics. We can do summary statistical version. Of course, this is not exactly summary statistics, but to explain, we call it nuclear mapping, but it's very close to summary statistics. If it's summary statistics, this is a y and a theta. But we were using that because y depends on y choose. So that's kind of hard. So let's do the t. It's kind of the mapping from the noise space, parameter space to some sort of q, typically a lot smaller than n. And then that's kind of, you can do that. And next, I'm going to give you an example to tell you how we did it, actually, in a particular example. If we do this, and I'm still using this broad set, of course, I depend on theta, potential theta. Then for each potential theta, I create a broad set for this TU theta. Then I kind of construct my confidence set using that same way, do the inversion, same way. Then this is basically inverting the broad set again. To do that, that's guaranteed to do that. And then this kind of artificial, why we call the Repro sampling method, Repro samples method is that it's a fake data. Actually, beginning I was saying to fake data. I was talking to Nancy Reed asking, I say, I have an idea to do using artificial fake data to do it. They say, don't use the fake data. You should use something, it's too negative. You was thinking of something better. The statistician is always negative. So that's kind of eventually we settled on the Repro samples method. Repro is reproduction, so it's artificial, same thing. It's similar to knockout, right? And then this is Repro samples method. And then that's how you do that. And this kind of nuclear mapping function actually has a connection to the test statistic when we do that. When indeed we can choose this as a test statistic, then this is kind of very close to the Neyman-Pearson. The broad set is corresponding to relate to acceptance region, and the method is very related to Neyman-Pearson test. So you can see that connection of that. And then this procedure is called Fisher-Dempster inversion, because this kind of solving these things is inversion. Why we say it's Fisher-Dempster inversion. Dempster-Shafer calculus talk about the inverting a set. This is actually indeed has a flavor of inverting set. So I give the talk in the BFF community, and some people say, maybe you should call it Dempster-Shafer, the Fisher-Dempster inversion instead of just the Fisher inversion. So that's kind of distinguishing to the Fisher's fiduciary itself version. So that's kind of we refer this as with a set, inverting a set as a Dempster-Shafer, Fisher-Dempster inversion. So this is give you an example. So that's how you see that why this works well. So basically, it's a very simple one. Suppose I have binomial model with a very small p or very large p. So there's no asymptotics, right? N times p less than 5, or n times 1 minus p is less than 5. You don't have, that's rule of thumb. You don't do the asymptotics. So, and this binomial model is very easy to write this kind of data generating form. You have uniform 0, 1 and do that. And with that, then I have observed that some sort of data, then I can kind of say, hey, that's setting my nuclear mapping, the test statistic as this form. And then this is one, for any given theta is a binomial. So it's with this binomial, I can get this borrow set lower bound, upper bound very easily. And I'm going to give you that next slide to talk about how you do that. If I get this kind of a borrow set, which is an interval, together, put in here, then I can simplify it. Then eventually my confidence set, in this case, solving this equation, it becomes my y observation is between this lower bound, upper bound. So that's if the theta, my try the theta, give me lower bound, upper bound, and y observation is between that, I'm keeping the theta, otherwise I don't. So that's the next is the example of that. So suppose my choose is binomial, my choose is my n is 20, and my choose is 10%. So 20 times 10 is equal to 2, less than 5. So you don't have a water test. Water method is not good. Water method don't give you good confidence interval for the choose of 10%. So that's kind of very bad coverage. So what our method is going to do, so I don't know this choose is 0.1, so let me try 30%. I don't know whether 30% is in the interval or not, but let's try 30%. For my 30%, then this is a binomial. So this is a bar chart is binomial of n equal to 20 and the probability success of 30%. So this is a bar chart. Then from this bar chart, you look at the borrow set, you look at, hey, what's the shortest intervals is between 2 and 10. The area on the shaded area is 95, more than 95. So my lower bound of this one, A lower is 2 and the upper bound is 10. Now, if my y observation is between 2 and 10, I keep this 30%. Otherwise, I throw it away. Does that make sense? So then that's the one is that. So I don't know this choose is 10%, but let me try 30%. If 30%, I get a lower bound, upper bound. If my observed y happen to be like 9, then the 30% I should keep in the interval. Otherwise, I throw it away. So that's basically that. So it typically 20 times 10 is about expecting y equal to 2, right? Y equal to 2 or 3. So if y equal to 2 or 3 is belong 2 is here, so I can still keep it. But if you observe y equal to 1, then the 30% shouldn't be there. Okay, so that's basically that's kind of idea. That's how we're getting these intervals. So you look lower bound, upper bound. If it's observed the one is between these two, I keep it. Otherwise, I throw it away. The nice thing about this example, I don't have nuisance parameter, but it tells you how we quantify things. Okay, so the things actually in now data science is a lot more complicated. So basically, there's a nuisance parameter we need to deal with it, and how do you do things. And then particularly, I have today I kind of highlighted important one is I have discrete parameters. Regular conditions does not happen. So this is kind of we have a bunch of the framework is a very generic general idea we already talked about. And then the things is how we really deal with this very complicated tree model type of things. So in particularly, we look at this non-trivial inference problem. Suppose that my parameter is mixed type. I do have discrete parameter and continuous parameter. How do you do that? Like Gaussian mixture model, or this is a tree model. This is a tree partition, and this is a leaf, each leaves parameter. If I give me a tree, give this particular tree, and then I'm a leaves parameter over that. So this is the two tricks we kind of realize it's very important. The first thing is that I need to separate these things to do them together is very complicated. It's very hard. So we do them by steps. So first step is that we handle this discrete parameter and get a confidence set of discrete parameter, and then treating this continuous parameter as a nuisance parameter. So after that, then I handle this parameter conditional on I know which gamma 0 discrete parameters are. So this is kind of dissect the complicated problem into the manageable steps. So that's very important that we realize. A second thing is that this is actually one trick. Another trick is the Fisher inversion technique I'm going to highlight is that the discrete parameters, suppose screening, we can use the property of discrete parameters to screening the space to reduce our computing to be able to get a confidence set of the discrete parameters, 100% confidence set for discrete parameters. This is actually indeed of taking advantage of a discrete parameter space, and then instead of a disadvantage, turn the disadvantage of lack of theory inference become computational efficiency. Let me just started with the second techniques. This is a kind of also linked to the optimization problems. So basically what say, hey, I suppose I have a tree. This is kind of, again, I'm talking about that. And then this particular difference is that realization observation from parameter and the realized error. And then this particular parameter, including two types of parameters, discrete and continuous, or this could be any kind of, even discrete is fine, but kappa 0 is our interest of discrete. So what we do is that we try to find a data generating inference. So basically, instead of the trees have, or maybe use a high dimension regression, high dimension 2 to the p choice of models. And instead of looking at 2 to the p, which is huge, 2 to the 1,000 is huge, then that's to reduce the space, search space by using this data 100% confidence set. So that's basically what we do. So this thing is actually there is inherent. So this is our equation, the data generating equation. This equation holds equally. So you know that if I look in this optimization problem, there's a connection to the optimization problem, algorithmic program. Because this is, if I choose kappa 0, choose C0 over here, this is equal to 0, the loss function, right? So you know that kappa 0 is one of the solution of the choose of the model. These things apply not only just for the L2 loss, and there could be any loss function or penalized loss functions with that. If your choose is over here, so that the catch is there. If I know the real error, I would always getting my true model out by the optimization, because you true model over here, true parameter over here, you're generating the loss function is 0, right? It's basically our smallest. So this is a loss function, can be any kind of properties. But then the problem is that I do not have this U real. So the fiducial, Fisher actually started to talking about that recent fiducial is that say, instead of using R real, let's use U star because I know the distribution where U real coming from. I just generating a U star. And then use this artificial one to replace the true one. And I can generating the kappa star over out here. So, and this kappa star, of course, not necessarily equal to truth. That doesn't necessarily equal to true one if these two are different, quite different. But the nice thing is that you notice that this is a discrete parameter space, and this is a U typically is noise is a uncountable space like a Rn, and this is a discrete parameter space. So there is a many to one mapping corresponding to here, right? You have many U star while getting you same kappa star, because this space, this mapping is from this space to this space is many point. It's uncountable set to the countable set. So that's definitely you have many of them will be the same. So in that case, that you would know that this in many applications, these things this set is not empty. Basically, we could saying that is that I know that as long as I have U star is in the neighborhood of these things, this one will give me the true value. So I do not necessarily to get to the wrong one. So this is kind of illustration of that. Typically, we use angles in the regression, the tree models. So if I do know that this is U real, this angle of distribution in this Rn space, you can thinking of that. Then there's an angle. There's a pi is space. As long as you start coming from in this kind of area, in this angle, cut in, then I know that this optimization problem still give me the true trees or true number of models. So that's basically, that's what you have. Then the question is that, of course, I do have some others which doesn't give me the right place, doesn't give me the true one. But I collect all of them together, and then you know that I collected all of them together. If I have this M, I'm repeating this many times, many U stars, one of them going to hit it. One going to hit inside the pi, right? You're generating randomly, and one of them, just naively thinking of that, one of them you will be inside because the probability space is not 0. And then you can M large enough, then you know this contains the true model. That's kind of general idea. Okay, but then of course later on we'll talk about how you're cutting down the set as well. So that's essentially, you can then mathematically you know that as long as there's a pi, as long as this set is bigger than 0, typically for this many to one mapping, this holds, and this condition holds. If this condition holds, then I'm generating many of this artificial data. One of them is going to be in the neighborhood of real noise, and I can get the confidence set out. So that's basically, that's kind of idea doing that. After you get that, that's basically the 2 steps. Maybe let me skip that one, just talk about trees. So basically, I'm using this kind of Fisher. The second one is called Fisher inversion method. So Fisher inversion, this is more directly related to fiducial method. And this is kind of a fiducial method. What we do doing that is that construct the data dependent this kind of candidate set. First, I just using this Fisher inversion method technique 2 to get a confidence set, 100% candidate set or 100% confidence set for the tree model. And then for each of the tree model in this, for each of the trees in this collection of confidence set, we can construct confidence set for this predictions for my predictions, and then combining, assemble them together to get the inference. So that's basically, that's kind of idea of doing these things. Let me just particularly look in the trees, what happens, okay? This kind of, before the last few slides. Yeah, sure.
Cool.
Mm-hmm.
I guess let's say like the U relative is like n-dimensional, like n samples.
Right.
Like you want to get close.
Mm-hmm.
So do you have, I mean, as n grows, you're going to have a sample on.
Yeah, that's a very good question. There are several things. Is that one is signal, how much signal you have? And the second thing is that when n is large, how much things of that. We need to calculate all these things. But in general, n is large, actually, then this pi will be getting bigger because you have signal. Basically, you look at the signal, how strong your signal is. That's how big the pi is, depends on your signal. Depends on how strong your signal. Your pi is n gets bigger, it seems the signal become bigger, easy to identify. So the pi going to
like, do you have a sense of how?
Yeah, we do. In the high dimension regression, we did have that. Yeah, we do have the result. How big the size, how characterization of that. Yeah, yeah. So yeah, that's pretty good, very good question. So that's basically a regression tree. So that's kind of coming back to what we were trying to do. A regression tree is that the membership. And one thing I want to emphasize, that noise, I don't even know the noise. A lot of people assume it's normal noise, something like that. In our paper, actually, we're working on the paper, which is sub-Gaussian. In fact, other distribution is okay, as long as the second moment, mean zero second moment, that the error is okay. Okay. Sub-Gaussian does, yeah. But what we're particularly working on in that paper, the manuscript is on sub-Gaussian model. So the goal is that how can I do inference, get confidence set, confidence interval for this prediction for the expected Y for the tree model. So that's basically what we're doing. And then this, of course, the existing method is single tree. Single tree is interpretable, is very nice interpretation, but not counting on the tree estimating uncertainty. If you, I think, you can do post-selection inference, but then again, it's a little bit different. So often a tree has often larger bias leading to invariant inference. A larger sample ensemble method as kind of now people have been using that. The nice thing about this is greedy is that you have consistent estimator, but this has become a black box because of 1,000 trees. You don't know how to explain them. And second thing is a greedy method. You do need to have asymptotic huge numbers and to be able to work. And also this enlarged confidence interval. The part of the reason is that we're thinking is that because you do have a bootstrap resampling kind of method involved, you introduce artificial randomness into that particular program is not controlled. So you need a strong assumption and things like that. So to talk about this point, we just getting back to the toy example, we talk about 3 leaves. And this is another presentation of the example. We look at the 3 leaves of these parameters. So you have true partition is these 3 groups. And then we're looking at the 2 points, looking at the simulation to kind of highlight what we're talking about. You have 2 points. This point is in the middle of this group 3, so it's easy to get. And this point is kind of on the borderline. It's harder to catch. It's a kind of harder problem to prediction. So the result, you can see that this is kind of use the inference coverage results. We're using, I still thinking is that 300 repetitions. So if you do the prediction of this easy point, when n goes gets larger and larger, actually the post-selection inference, the blue lines, is getting better coverage eventually because you have enough information to classify this group into the group 3. So then that's kind of nice to have that. But then for this boundary count, even with the n goes to 800, is still under coverage. It's about less than a little bit around hovering around the 90%. It won't be able to get anywhere. When n is small, of course, everything is not there. If you do the random forest use bootstrap and then use bootstrap. I think this is using the Stanford group's algorithm trying to do that inference. Then you can see that the coverage of green one, even the good ones, you need to have larger n to get there. If it's the bad point, it's a harder point on the borderlines on this kind of place to separations, then you do need to still have kind of even 800 is not enough. And then as far as for the length of the intervals, then you can see that the single tree is always good because it just undercounting this uncertainty. And ours is kind of gets larger and get worse. And then the random forest actually method usually don't give change as much. That's part of the reason probably is that there's kind of uncertainty on the resampling. It's very hard, even when it goes large. It's not easy to getting done. But anyway, so that's kind of empirical results give you some sense of how comparison. So how we did it is that let's going back to this tree model. And with this tree model, and then our target is that. This is the slides we talk about that. And then the U again is just a sub-Gaussian noise. If we use the off-the-shelf algorithm to do it, we can just writing in this way. Of course, the usually is not writing in this way. Just for simplicity, we're using this tuning parameter penalty to write it in this way. So you do need to have some sort of penalty to look at complexity of trees. So that's kind of you're fitting the off-the-shelf is doing that. The off-the-shelf typically you this y minus this expected value of the model, right? Regression. The noise is not here. So that's basically that's difference what we do. That's kind of typical one. So what we do is that recall that if I know the noise, I can get the truth. So that thing is that really I can recover the truth if I put the noise back into the conventional algorithm. Conventional algorithms don't have a noise. If I inject the noise back into the subtract from the y, then I will this become a denoised noiseless like kind of fitting models, and I will get truth. I will be able to get truth. That's the fact. If I get the truth, but then the question is, I don't know this generating from sub-Gaussian noise. So what do we do is that say, instead of looking at that one, let's look at the star, epsilon star from standard Gaussian model. And then I put this epsilon star over here, put the sigma over here. Sigma is kind of look at the scaling. You just care about the length. Angle, don't really care about the direction. So this is kind of another slide. So we're talking about the other same kind of pie chart we're looking at. So my truth realization is this bold one. And then what I'm doing is that I'm using the Gaussian noise, independent Gaussian noise, and I standardize it. It's on the ball, right? So that's the direction. Then you could have other directions. And the one direction, the red one is close to the blue one, then I can get, if this is kind of angle, you look at the angle is, this cosine is larger than, it's close to 1, then this angle close. If these are close, then I will be able to prove that. And well, I can kind of generate many of them. One of them is to be close. So with this capital M, and many of them generated, I can prove that as long as M goes to infinity, M gets larger and larger. I know that one of them is going to be controlled, not belong. I don't contain any of them. Or I can, this truth belongs to this set is big equal than 1 minus this. And this quantity goes to 0. Doesn't belong less than 0. But anyway, so this gamma is that kind of angle what you control. So did I have, I think I lose the pointer. The loss of power. But anyway, yeah, so that's actually this angle, this gamma is corresponding to that one. So it's how close the angle you have. This kind of controls what's the high probability you contain the truth or not. But then there's another catch of that one. This one probably is that M gets very large, you get many trees. The other catch is that when I fit in the tree, I can also have, when I fit in the tree, I can also fit in the beta and the eta. So by the way, when we do this tree models, right, I can fit in this one. I can put this epsilon star as part of the coefficient. So I can use conventional kind of off-the-shelf algorithm, treating this epsilon star as another X, and then put this regular, can use existing tree model fitting algorithm to do it, okay? So this epsilon is additional covariate, and then do it. I don't need to write in my own code. So, and then when we're doing that, then we would have kind of fitting the trees and the betas and sigmas. That's kind of everything is fitting. And with that, we can look at the angle, look in the residues of y given this fitted the tree. the beta hat. And with that, we will be able to getting the so-called working residue. And this working residue turned out to be is a linear combination of this angle, of this epsilon star, I simulated one, and then the real one, which I don't know. Okay, which one I don't know. So you look at the cosine of this one, actually can be controlled by this epsilon and the delta. In that case, that I can calculate after I can simulate the epsilon star, and also I can calculate the delta, which is working residue after fitting. Then I can control how the angle of these two. And if this angle is small, I keep it. Otherwise, I throw it away. So that's also, I have another filter of that, so to get the model out. So with all these things, we will be able to getting like trees, confidence set equal to 50. So the principled tree selection is that I get a trees and then I generate noise, and then my data probably noise is not necessary to be normal. I still use normal to generating it, and I can getting the tree fitted and also working residue. And I screen that if the working residue and the generated epsilon noise, if the angle is small, I keep it. Otherwise, I throw it away. So that's basically I'm keeping that. And for each single tree, I can getting confidence intervals of this quantity of target. And after that, we can ensemble that. Ensemble actually aggregating, we just use very naive, very simple one, just union of the intervals. So this is conservative. If there's room. If people want to do the model averaging, that would be better. Yeah. And then that's kind of, we have theory to guarantee the coverage. Mathematically, you have that one. This result actually is a finite sample result. Anyway, so probably I can wrap it up like 5 minutes. Then I just skip the last example of causal inference example. So basically what we do is that we do have the artificial randomness is generated by resample. Instead of doing the bootstrap or subsampling, what we do is trying to simulating epsilon star, mimicking the U real. So this is more targeted. So it's not going everywhere. So that's kind of evidence you can see that our trees, when you do the prediction, is always around the truth instead of spreading around quite a bit. And the second thing is that the small number tree are required. So this is also interpretable for the interpretations. You have 1,000 trees, it becomes black box. If it's 50 trees, you can ask the expert to say, hey, this is 50 trees in the confidence set. Which one is the good, making sense in biologically or social science sense? Then you ask them to check. So that's basically that. And then this, I'm going to, for the interest of time, I'm going to skip the last slide on the causal inference. So basically, you can kind of extending the framework to do the causal inference to make. Let me see. Yeah, to make causal inference setup to do the average expected well IPW, yeah, inverse. It's this. Yeah, average treatment effects, the conditional average treatment effects. So anyway, let's just skip that. And then let me conclude that talk is that repro samples method, what we talk about, I hope you kind of see what we're up to. And then this is kind of trying to, very intuitive. It's kind of try to make common sense. And then this is with theoretic guarantee. And then can handle very complicated discrete and non-numerical data. And then is effective for a few, at least what we worked out as works well. One thing I probably want to confess that I didn't mention here is computationally more expensive because I need to fitting many of you generating the models. And then the principal random forest, we can small set of trees, and then we can also is more interpretable and tackle the black box issues somehow in that direction. And the second thing is effectively answer the inference problem of actually while accommodating estimating uncertainty, tree uncertainty. So empirical performance is actually better than the existing method. And then anyway, so before I kind of let you go, I want to do one advertisement. This is a book. I mentioned that we come from the Bayesian fiducial frequency framework, and then we finally getting a book, handbook come out, published this year. So it's kind of doing that. One thing I want to highlight is I want to brag on one article what I have. Well, before what I want to say, there are a few articles I want to point it out. It's worth to read if you get a chance. The first one is the Nancy Reed's article on the chapter 3, talking about the Bayesian fiducial frequentist, that kind of distributional inference. You can put them together. And the other article I want to emphasize is the Volodya Vovk is conformal, the guy who proposed the conformal prediction. He actually had this kind of idea. He said the conformal prediction comes from the inversion idea, Fisher's inversion idea. So that's the article you talk about, the fiducial kind of behind how he started with the Dempsey-Hill problem of the conformal inverse. So that has a connection of that. So this is a good article to look at that as well. So one thing, as I highlighted, another one is my own article trying to understanding the connection between Bayesian fiducial frequentist. And one particular things I want to brag about is that I don't think many statisticians have article published in journal of in philosophic journal. So this is an article we got from philosophy journal. It's just by coincidence is that this BFF kind of workshop every year, and then Xiaoli from Harvard, Xiaoli Meng from Harvard, he always insists to have a section for the philosophers. And one of those workshop, my student, Suzanne Thornton, had a poster on this kind of connecting Bayesian fiducial frequency together. And then the philosopher liked it. And then so invited us to their version of GSM to give a talk. And in their version of GSM, after talk, and Suzanne gave a wonderful talk, and afterwards they say, hey, do you guys want to have submitted an article to our journal? So that's what happened. So this is, I don't think I would ever get a chance to write another one, but I want to know many people did that. I want to show it. This has just come out. Yeah. Thank you very much.
Hey, we already have questions.
Yes.
Thank you. This is really great and really engaging. I wanted to understand where the Repro sample procedure differentiates itself from the generalized fiducial inference setup. And I was trying to think about how to frame this. And one way I was wondering about is maybe would it be fair to think of this as kind of like a profile likelihood based approach to generalized fiducial inference, in that, like, in profile likelihood, you care about, you have a nuisance parameter that you're trying to not care about and find a way to get valid inference doing that? Or is it a better way to think about it in that towards the end you had like it's an inversion, but you're conditioning on the cosine between delta and that's the line to be, or is it a fiducial inference, but it's conditioned on that?
Yeah, okay. Very good question. Yeah. So I know we chat, so I know you have fiducial background. Fiducial part of it is this site. Then if you use Hannick, the generalized fiducial, they use this as a fiducial distributions. They're collecting those things and then don't have any content and collect this as fiducial distributions. Right, that's how you do that. And then they didn't particularly specify on this discrete version of that. That's anything they do it that way, called fiducial distribution. And then they do that one. They do not check the frequentist coverage. That's something different what we do. We actually really checking, this is coverage, is frequentist coverage. It's not fiducial coverage. The noise, random noise, what I didn't point it out, is the sample noise of your error noise. The gamma is actually conditional getting the noise from the artificial sampling you use stars. So that's different. So suppose in the tree model case, this sub-Gaussian noise, and this is you generating from Gaussian, this Gaussian noise. So that's kind of say, hey, given a set of Gaussian setting you're getting, and what is the coverage of that? So they didn't prove that thing. So this is something it's new from the fiducial. Fiducial only have a fiducial uncertainty, don't have frequency uncertainty. I care about frequency. I did proof of frequency uncertainty. So that's the difference from that what we do. So they just use the fiducial intervals, but the fiducial interval does not guarantee the frequency interval. That's yeah. That's the one. Yeah, the fiducial does not guarantee the frequency coverage. We do have a flipping to the get frequency coverage. So that's something we did additional on that. But we did use their technique of the fiducial inversion. The fiducial is there. Yeah. Thank you. Yeah.
I have a question. So to obtain these guarantees,
Mhm.
you need for every model to derive a specific condition, just like we did for the tree.
Mhm.
Or yeah, so I guess it's
Yeah, that's probably true. Because different models have different model complexity. How you like we do need to have play the games between the how close this is to that. You have mathematical write it out. You need to have concrete situation to write it out. In general, I think its formula is going to be very complicated, very hard to write out. Otherwise, I won't be able to write theories like this. Probably you have these things like this.
is because
Yeah.
like on the normal, but you want to show that that doesn't matter.
Yeah, it doesn't matter. Yeah, that's one of the thing of that. And or if I don't simulate from normal, I simulate uniform, then the form will be different. Yeah, yeah. That would be different. So that's mathematical. You write out how to see, understanding the control, the power, how the sample, artificial number, bootstrap sample size will be is related to control that kind of errors terms. Then you would have some sort of concrete, really concrete distribution to work on. Otherwise, that's very complicated. Maybe someone later in the future will be able to do something. So far, we have to use just the very using that, yeah. Concentration equality for different. Which sigma? The variance. Okay, so in this tree, actually, it turned out to be sigma. I don't really care. I just this direction, right? This sigma is this. So you can think of this as if it's this is kind of 1x, is beta times x. That's kind of regression, right? Beta 0 plus beta 1 times xi. And this one is beta 2 times x2. They're treating this as x2. Then this is kind of when you're fitting it, it's going to automatically, the algorithm will fit the sigma as another beta. So that's kind of, you can do the regression. And with that, actually, I really don't care about the sigma. It just give you just scale you up and down a little bit. I really care about is not how big the magnitude of the angle. I really care about is that is the angle is close. If they're close, I know they will get choose. It doesn't matter. I'm going this long or this short. So the sigma, we really don't care about that. So it's just to make it easier to handle that. Because when I could have sub-Gaussian or even other kind of distributions, and then I don't need to worry too much about this parameter. Yeah, that's part of the thing we kind of worked out. That turned out to be easy, and the computational is easy. Actually, I was talking. Qi Yao is from London School of Economics. He was asking me, was in Hong Kong giving a talk. He would say, fiducial inference or fish inversion idea has been long for such a long time. Why now become suddenly popular? And then why you will be able to do it? I say part of the reason there's several things. Of course, those giants people are fighting with each other. That's always cause the issue of moving forward of different methodology. The most important one actually computing. So before that, the computing is not easy to get. But now actually, by computing, I just need to use the off-the-shelf algorithm. I don't need to develop myself. There's a connection between this inversion, as we mentioned here, inversion to the optimization problem, and then we can get that one directly getting that one. Yeah. Yeah.
Okay, guys.
Yeah.
Last question or two.
Go ahead.
Yeah, you know, okay, so maybe somebody else was when I have
For parametric, for continuous parameters and parametric models, if you compare the confidence intervals you get here versus like the optimal one, how do they compare?
Well, actually, this is actually going back to the our point of that. We did have okay, maybe I should show you the reference. We did have examples to show this. It's actually, if you have an optimal one, we can get optimal one too. Oh no, not this slide. Next. Yeah. Neyman-Pearson method, right? You have Neyman-Pearson method. And then if the classical test method is optimal, you can get inverting to that to get confidence interval. Inverting testing, the Neyman method to get the intervals. And if it's optimal, we definitely can get the interval optimal. We do have that paper actually we submitted JASA and then it's too long, so we put that result in the appendix. And then, so this is the reference of that. It's still under revision. So this is this paper in there. They have this connection to the Neyman-Pearson test in the appendix. And with the appendix also, you do have examples saying that we do better. We have actually example. You don't get optimal results like a ratio test. Don't give you an optimal result. We will be able to get the optimal results. Yeah. It's a continuous setting. Yeah.